Hello, I'm Anna Mackay and this video is called Geometric Sequences and it's the second one in its pair. So, carrying on from last video, the geometric sequence formula is what? Tn was equal to, now you have to excuse the font on this one, I'm having slide issues, hopefully it's just this one. It's the first term multiplied by r to the power of n take 1. Hopefully you remember that one. If not, write that down. So this is often referred to as the explicit formula. And the other version of it is where we're thinking about the n plus 1 term, so the second one along. That is the previous term, Tn, multiplied by that common ratio to work out what the next term along is going to be. In that case, we must state T1 because there could be many sequences with that pattern, but we have to define where we start, and that is called the recursive formula. Just a reminder here that the ratio is calculated by taking the next term along multiplied by the one before, divided by the one before. That's how we work out the common ratio. Whereas in arithmetic sequences, it was a common difference. This time it's a common ratio. So an example here. We're saying that these are consecutive terms of a geometric sequence and we have to find k. So having a think how we're going to do that, thinking about the ratio, the common ratio that would exist between these. So there's that formula that if we divide the n plus 1 term by the term before it, then that will give us r. These two equations here come from this term, the 2k term, divided by the term before, the k plus 1 term, will give us the common ratio. We don't know what k is, we don't know what r is yet, but that fact still remains. And then the same technique for this term, divided by the one before, will give us that common ratio. And now they are both equal to r. R is the subject, so we could work with that. We put them equal to each other. So by doing that, here's it written neatly, because they're geometric, that the ratio will be the same. Now we need to use our algebra skills to rearrange that. You're going to cross multiply there and see what we get. We get 4k squared equals that multiplied by the denominator there. Now you have to expand that bracket and you would get 21k, subtract 21, subtract k squared, now it's add k. Written out neatly for you is that. Collecting like terms and rearranging so that all the unknowns are over to the left and make the right hand side equal to 0. You could do it either way around. I quite like to end up with positive values of k squared, so the coefficient of k squared is positive, which means taking that over there to add on k squared and taking everything else over as well. And we end up with 5k squared, take 22k plus 21 is all equal to 0. Now, that's a quadratic. How do we solve quadratics? Cast your mind back to the different techniques you know for solving a quadratic. What's the technique that always works? When in doubt, the quadratic formula. So we need to set this up. Here's the quadratic formula. I won't say it out loud, you should know it off by heart. Thinking about what your a, b and c are here. A is the coefficient of k squared, so 5. B is the coefficient of k, negative 22, and c is 21 there. So then we have to substitute them into this formula. Calculators to help you out here, and because of the plus or minus sign we get two values for k, and that's fine. That could happen. There could be two geometric sequences where that happens. So we have technically solved the problem, which was find k, so we could stop there, but let's test our answers. That's a really good skill, a habit to get used to doing. Then you can know if you've got it right if you're in a test situation or something. So that means we need to substitute those in. So if k is 7 on 5, therefore we substitute that into each term. So we get 7 divided by 5, take 1 for the first term. That gives us 2 on 5. The second term is 2k, so we have 2 times by 7 on 5, hence you can see the 14 on 5 there, and so on. And then looking at the common ratio, seeing if there is one. So then you just need to do a quick divide of subsequent terms and to see if you get the same ratio between those terms. And you do. And the other version is when k is equal to 3, you substitute in k. So if we have k take 1 for that term, you do 3 take 1, that gives you 2. That's that term there, and so on. And then a quick division between the terms gives you a ratio of 3. It's okay for those ratios to be different numbers in case that's what you're thinking. Don't feel that you've got the wrong answer because you've got different R values. That's fine. That relates to, because we've got different K values, that the sequences would be different. And so that's okay. Alrighty, just a quick refresher on some power laws here. If you had to solve for R, undoing that power there, you would do the square root. But you would know that you need to account for the plus or minus version, the positive or the negative version. So R could be plus or minus 2. What have I got there? So that's fine. The next one, the cube root of 8. Having a think what your answer is going to be there. Do you have to account for the positive and the negative? So R would be positive 2. Could it be negative 2? Could R be negative 2 and end up with a positive value of 8 there? No. Have a think about why. A couple more. The 6th root of 64. So that's a skill you can do in your calculator, or just out of interest, these are also calculating that. This time we do need to account for the positive and the negative version, and we get plus or minus 2. We have to take it into account there. One more, the cube root of negative 8. So, sorry, R cubed, what is R? So in this case, the cube root of negative 8, I was right, negative 2. Did we have to take into account the plus or the minus there? Having a think of R equals negative 2, if you cube that, you would get to negative 8. Is there any way that you could get to positive 8 if R is negative 2? No, because so when should this appear? I'm hoping you're realizing it's when it depends on the power. These powers are even and these powers are odd, and because of that, I'm sure you know where I'm going with this, that if it's an odd power, therefore we would have 3 negatives, so it's an odd number of negatives, which means we would end up with a negative. If it's an even number of negatives, it could end up being a positive number, which means we therefore have to account for both answers there. Hope that was a quick refresher for you. Hope that made sense. A couple more questions here. A geometric sequence has T2, the second term, being negative 6, and the fifth term being 162. We have to find the general term. Right, we don't know the starting term, and we don't know that ratio. What can we do here? So we do know that the fifth term is 162, and the formula for any terms using our explicit formula is the first term multiplied by r to the power of n take 1, so to the power of 4 there, and we know that's 162. Let's set it up for the same way for the second term. So it's going to be t1 times by r to the power of 1, and that's equal to negative 6. Now, unlike simultaneous equations you've done in the past, that gets trickier. But let's set it up that the ratio between the terms will be the same. So what I mean by that is, well, we can class them as two equations still. Having a look here, the ratio of that fifth term divided by the second term in that formation must be the same as the constant values. So we have 162 divided by negative 6. I hope that makes sense. So we've done term 1, formula 1 divided by formula 2, having a think what happens. The T1s cancel out. Using your powers laws, 4 subtract 1 is 3. Doing that division gives you 27. So we've got r cubed is negative 27. What is r? Now you can see why we did that work on positive and negatives. It's the cube root of negative 27. So will it be a positive or a negative number? It will be a negative. So we've got r. To find the general term, we need r and the first term. So the technique to do is take that r and substitute it back in to either equation. Pick the simplest one. So pick term 2 because there's no power of r there. So this came from the T1, r is equal to negative 6. And now we're solving for T1, which is 2. Go back and answer the question. Find the general term. So you must substitute those numbers back in to get the full answer. And there's our general term. Okay, I still have one more, I think, to go. We've got same idea. I might whiz through this a bit quicker. Feel free to speed me up. So the fifth term is using the formula, whereas r to the power of n take 1 is equal to whatever T5 is, 150. So we set that up. Next, T3 is equal to 6. Feel free to pause this, try it yourself, and come back and check if you're right. We've got the two equations there. We're going to divide the terms because, you know, if you imagine you've got T3, T4, T5, that the amount of the ratio between those will be the same whether or not you're working in term notation or the actual value notation. 150 divided by 6, and cancelling out the t's, using your power, so you're going to get r squared is equal to 25. R is equal to plus or minus, this time, 5. So in this scenario, you have two sets of r. So substitute that back in. Again, I recommend using the slightly easier one, r squared. So you substitute in, you could run it separately. You could do one with r is 5 and one is r is negative 5. That's fine. But see what happens here with the square, it will become the same number, 25. Solving for T1, you get 6 divided by 25. Don't stop there. Go back and answer the question, which is to find the general term. So we substitute that in. It is worth noting here that you need to write this in two ways because you had two r values that this is exactly the same formula but with the r with a positive 5 and one with a negative 5. Last one, I think, using your calculator to find the first term of the sequence that exceeds 1400. So to be able to work that out, you need to define your sequence. Our first term is T1, and then we need the ratio. How do you get that? You look at the difference between these. So if you divide the second term by the first term, what are you going to get? Square root of 2. We can now construct our formula, our explicit formula, and substitute the numbers in. Now, so we need to find n such that this whole thing exceeds 1400 without sitting there and writing all of the terms along to see when that happens. So, using your graphics calculators here. So, in equation, you can put this formula, which as you can see is our explicit formula here. Noticing how we put in the power, we use x, and you can then go to table of values and that will connect up to the equation that you've done. Might be a new technique that you've done before. Here's what it should look like on your Casios. Here's our formula at the top. You need to scroll down so that in the y column you find the first term that exceeds 1400 and that you'll find that it's the 17th term. It doesn't matter that it doesn't equal 1400, it's the first term that exceeds that. And so you would write the first term to exceed 1400 is T17 and state what that is. Phew, that was a long one. The next one in this series is called compound interest. Thank you.